today's demonstration, we will look at the Xilinx IP for peak to average power reduction or crest factor reduction and digital pre-distortion. The RF power amplifier represents one of the biggest challenges in addressing the energy efficiency of the 5G RAN. The power amplifier, the RF power amplifier, can consume between 50 and 80% of the energy in the radio. So it's no surprise that it is a source of research and constant innovation to try and improve the efficiency of the power amplifier. Along with these new technology developments, mobile network operators are also looking at new architectures or ways of sharing the equipment in the RAN, so-called MORAN. All of this poses a challenge for the RF power amplifier, and Xilinx's adaptable and scalable IP to improve the energy efficiency of the power amplifier is a topic of our demonstration here today. Specifically, we will look at our configurable crest factor reduction and highly configurable DPD solutions. These solutions can scale to address a wide range of use cases and support your needs into the future as the technology evolves. Today, we look at a particularly challenging use case for digital pre-distortion. Here I have a representation of a 64T64R massive MIMO panel. On the left, we can see a situation where the operator can deploy carriers or instantaneous bandwidth over a wide range of frequencies, in this case between 3.4 gigahertz and 3.8 gigahertz. That provides a lot of flexibility in the deployment. On the right-hand side, an alternative approach to address frequency allocations between two operators, A and B, some distance apart. Here we have a virtual split panel, two 32T, 32R panels, and in this case, the same radio, the same RF front end is used to support the diverse requirements and frequency allocations of both operators. The demonstration will use the setup as shown here. In a short while, I'll show you a video of the actual setup, but an overview here is it's based on the RFSoC Gen 3 family using our ZCU208 evaluation board, along with a Xilinx RF card we call XRF3. The power amplifier from Amplifier, this wideband LDMOS power amplifier, is connected to the lineup as shown. And we also use a PC-based GUI in order to control the setup. And a spectrum analyzer or signal analyzer will also be used to show the performance of the DPD. So here's a look at the bench setup we'll use for the demo today. This is the 208 board connected to an isolator. And here the isolator is connected to the DUT or the power amplifier module from Amplion, which is connected to a power meter. And here we're looking at the spectrum analyzer or signal analyzer we will also use along with the power supply unit for the power amplifier. This is the GUI we'll use to control the demo, and I'll show you that now. So this is the GUI. I can use the GUI to generate the test signal. In this case, it will be 10 LTE-20 carriers. So an instantaneous and occupied bandwidth of 200 megahertz has been generated here. There's the spectrum of the test signal. This will be fed into the CF4 and DPD. So now we're just going to unmute, and we're looking at the output of the PA right now. It's unlinearized, and here you can see the sample rates and the center frequency, actually 3.5 gigahertz for the DAC output. So that 200 megahertz centered at 3.5. So this is the same signal on the spectrum analyzer, again centered at 3.5, and we can see the unlinearized performance of the PA in this case. So now we will activate the DPD. We'll run the DPD with the power amplifier, and the first thing you'll notice is that the observation path is being displayed on the right-hand side there, and it'll linearize and converge, highlighted there with the purple box. So we can look at the same signal now on the spectrum analyzer. So again, we've run the DPD, and we're seeing the linearized performance as the yellow trace. The blue one was the unlinearized performance. Now let's look at the SEM. So just to show how much bandwidth has been linearized by this DPD at the moment. So you can see again, excellent performance here once we activate the DPD. So again, yellow is post-correction, blue pre-correction over a much wider bandwidth. So this is the output power on our meter. So 37 dBm is being maintained at the output of the power amplifier. Now we will recenter that 200 megahertz of IBW signal at 3.7 gigahertz. And we will just reset the GUI so you can see the signal there. I've got to recenter the signal analyzer now. So we'll take a look at the uncorrected signal centered at 3.7 gigahertz. It's the same power amplifier, the same setup. We're just recentering the signal. And again, we see the pre-correction performance. So now we'll activate the DPD. You can see on the right hand side the output of the power amplifier, the feedback path. And then we'll take a look at the output on the signal analyzer. So here we can see the corrected performance, the yellow trace again. So again, excellent adjacent channel power performance there. And for this, we will also take a look at the SEM far end. Again, we run the correction, which is post-correction is the yellow trace. And we can see the big improvements achieved. For more information, please visit the links shown here to find out about our latest RFSoC Gen 3 family and the ZCU 208 evaluation kit that we used for the demonstration today. For more information on the Amplion PA and products, please follow the link here.